Click the bell icon to get latest videos from Ekeeda.
Hi everyone, here in this particular video we will learn the AC analysis of CE amplifier. The AC analysis of CE amplifier is getting divided into two parts. One is with bypass capacitor and another is without bypass capacitor. Here in this circuit is of voltage divider bias. More than that, three capacitors are placed. These two capacitors are called as coupling capacitors. So we'll write this as CC1 comma CC2 is coupling capacitors. These capacitors are just placed to couple different stages of amplifiers. Suppose I want to have the first stage and I have another stage as stage number 2, which is in cascading nature with stage number 1. So this capacitor will not allow any DC current to pass through second stage. So as far as DC analysis is concerned, stage 1 and stage 2 will be isolated. So for that we have CC2 and CC1 placed in this particular circuit. CE is playing major role over here. This is called as bypass capacitor. This bypass capacitor is basically important to enhance or reduce the gain parameter of CE amplifier. This CE is placed exactly in parallel with resistance capital RE. So if we are talking about DC analysis, then we open this CE, DC current will flow through capital RE, but when we will go for AC analysis, scenario will be different. We will follow the steps for AC analysis and then we will arrive to have the requirement as far as AC analysis numerical is concerned. Keep this in mind that in your examination, they may ask you mid-frequency analysis. So mid-frequency analysis is also called as AC analysis. So whatever analysis we are going to learn in this particular video is nothing but mid-frequency analysis. Let's discuss the first step. First and important step is we have to short all the capacitors. Keeping capacitors short, it means that I'm allowing all the AC current to pass through all the stages. So if I short CE, CC1 and CC2, then what will happen? Input supply, that is nothing but VI, that is passing through the base of BJT, that is input side of BJT amplifier, and the output side is directly connected to collector side. CE is giving the redundancy for RE. So if CE is short circuited, then RE will become redundant and emitter will be directly connected to ground. So here we'll get to know the difference between DC analysis and AC analysis. In the DC analysis we kept CE open, so RE was there in the picture. When we go for AC analysis, then in that case CE is shorted and your RE is nowhere in the picture of AC analysis. So the first step of AC analysis is short all coupling and bypass capacitors. One more step in the step number 1 itself is we don't have to consider any DC sources. So we have to short the DC sources with their internal resistance. We have to convert that DC sources with respect to your internal resistance. So all the DC sources are voltage sources. So we have to short these voltage sources. Second step, nothing but DC analysis. question arises, why do we require DC analysis if we are going for AC analysis, right? But in the AC analysis, just in the previous video, we have learned three parameters, that is RE, small r pi, and GM. So all these parameters will get to know once we do DC analysis and once we have the value of IBQ and IEQ, and that value we will be getting only by doing DC analysis. So second step is DC analysis, right? Third step is nothing but draw AC equivalent model, and then we will go for AC analysis, right? So actual thing in this particular video is AC analysis, and for which we have to short all the coupling and bypass capacitors and short all the DC sources. So this DC analysis already we have done in the previous videos, so we will not repeat once again over here. We will start from this third step. Keep this in mind. Before starting third step, we have to short all the coupling and bypass capacitors, short all the DC sources, and how this circuit will look like. This CC2, CC1 will not come into picture, CE will not come into picture, directly shorted to ground, emitter and ground connected. RE will be redundant as it is VCC connected to ground. Then we will get to know that how your circuit will look like for AC analysis with your any kind of model. We will first modify the BJT in the form of model. So this is my BJT. This is emitter, this is base, and this is collector. Very nice. Once we have this BJT, what we'll have to do, obviously we'll have to do the namakaran for this. I have not given the namakaran for these two. This is because I have not yet specified which model we have to use. Okay, in any model we can get the same answer. So all the peripherals we will first draw. R1, R2 are connected in parallel. Yes, obviously this VCC is connected to ground and this R2 is also connected to ground, and one of the node is common. So this node also common and this node is also common. R1 parallel R2 will become RB, and RB will note it as at the base side. So it's in between base and the input. So we'll draw here this as resistance RB, and it is connected to ground. This is nothing but your input voltage, that is VI. This is all about the base side. What about the emitter side? Emitter is already connected to ground in the AC analysis, right? So we will directly connect it to ground. This is also connected to ground. About the collector, collector is connected to resistance RC, and then resistance RC is connected to ground because VCC is connected to ground as it is, and from collector we will be directly getting the value of output voltage. This is resistance RC, and here obviously we will be getting the output voltage. So this is all about your AC equivalent model. Either you can put R pi model, either you can put RE model, either you can put your H parameter model as well, no problem. Here we will be using RE model, and obviously we will convert this RE model into H parameter model so that all the values will be getting in all three models. Beta IB, this current is nothing but IB, right? And now we can do the analysis. I'm giving one basic fundamental for the analysis of any kind of amplifier. whether that is of FET type, whether that is of BJT type, CE, CG, CD, any kind of mode, right? We just have to understand this five finger analogy. Five fingers means what? Five laws we have to understand. First is Ohm's law, right? Second is KCL, Kirchhoff's current law. Third is Kirchhoff's voltage law, that is KVL. Third one is CDR, that is current divider rule. And fifth one is VDR, that is voltage divider rule. Once you know all these five fingers law, then we can easily go for the AC analysis of any kind of amplifier. So let's move towards the analysis of this kind of CE amplifier with bypass capacitor. First, we have to find out voltage gain. Now that voltage gain is nothing but represented in the form of AV, represented in the form of AVS, represented in the form of AVL as well. Now this S denotes that if we have any source resistance present, then we have to incorporate that source resistance effect. If we have any load resistance present at the output side, then we have to incorporate that load resistance effect in your AVL. So in general, the value of voltage gain is equal to VO divided by VI. Output voltage divided by input voltage. Now in this particular case, we neither have load resistance nor source resistance, right? So this is a simple task to find out the voltage gain. We will go for the five fingers. Keep this in mind that whenever we want to find out any voltage gain, then we have to go for the KCL at the output node. So this is one of the five fingers. This is your output node. Say we will name this as node A. I know that current flowing through this particular branch is beta into IB, and current flowing through this particular branch is nothing but voltage VO divided by resistance RC, right? So we will apply, we will be getting that beta into IB plus VO divided by RC is equal to 0. So sweet. We will be getting the value of VO in the form of IB, right? But IB is flowing through beta RE, that is at the input side. So here we are trying to move from output side to input side such that we will be getting the value of VO divided by VI. So VO is equal to minus beta inverse RC into IB inverse. That is nothing but, so we will be getting the value of VO is equal to minus beta IB into RC. Simple. Inverse, it's a simple mathematics. Now, let's say this is equation number 1. I want this IB in the form of VI. So we have to again move towards the input side. Think that I want this IB in the form of VI. What to do? IB is flowing through beta small re, right? And the voltage VI is nothing but voltage across RB, as well as it is same as that of voltage across beta RE. So very simple now. Now I can easily get to know that whatever resistance over here, this is beta RE, is equal to VI divided by small IB. So we'll be getting the value of IB in the form of VI, and it will make the things simple. We'll put the value of IB. IB will become VI divided by beta RE. Equation number 2. from equation 1 and 2, we will be getting the value VO divided by VI is equal to minus RC upon small re, and this is nothing but your voltage gain. Second thing that you have to understand is current gain. So current gain is nothing but IO divided by II. Okay. Again coming to this AC equivalent model, what we'll have to do, this is your IO, right, and this is your II, right. So a small change will have to make that. This is your II and this is your IB. So II is divided itself into RB and beta RE ka current. So I know that the value of this output current is nothing but this, that is current flowing through RC, and this current flowing through RC is exactly minus of beta into IB, right. And now this IB is acting as agent, dalal. So I can say IB is in between input as well as output side. So I just have to jump towards the input side and we have to find out IB in the form of II. Here another 5-finger law will help you, that is nothing but CDR. This current is dividing into two parts, one is through RB and another is through beta RE. Let's move towards the current gain exact analysis. I will say that apply KCL at node A. Keeping this in mind that VO divided by RC is nothing but your current flowing through the output side. So we will say IO is equal to minus of beta into IB. Equation number 1 for current gain. Now I want to dig out the value of II in the form of IB, and that we will be getting here. Again we will draw the pictorial representation. Beta RE, this is your value of RB, this is total current, that is II, and this is current IB. Both resistances connected to ground. I can say that IB is equal to capital RB divided by capital RB plus beta into RE. So here we will be getting capital RB divided by capital RB plus beta into small re multiplied by total current, that is II. Equation number 2. Now from this we will be getting the value of current gain. So from equation 1 and 2 again we will be getting the value of IO divided by II directly as minus of beta into RB divided by RB plus beta into small r. Right? Now if we consider the value of this is nearly same as that of RB, then your value will become minus of beta, and what we have gave the value of beta as a Namakरण, that is common emitter current gain, right? So it's a common emitter configuration, and here we have got the current gain, which is approximately in the form of beta only. So this is exact value that we have got for your current gain. So we'll name this as current gain. Third parameter that we have to find out is output resistance. This output resistance is simply VO divided by IO. A simple trick I'll give you from AC equivalent model. Just look from the output side, right? How many resistance that you are getting. If we take the resistance from the output side, right now I have only one resistance in my picture, that is nothing but RC. So here I can directly write down as RO is equal to RC, that is nothing but your output resistance. Now what will happen if we have the load resistance placed at the output side? Then if we have placed the load resistance at the output side, then the picture will become, this is RC, again this load is connected to collector as well, this RL. We can also have any DC motor, stepper motor, or any kind of load which is supporting your all the ratings of BJT. So obviously high voltage and high current load we cannot directly placed at the output side of CE amplifier. This is because it has some limitations of some current and voltage characteristics. So this is RC and RL connected in parallel. Now if we look from this particular output side, then we will directly get the value of RO as RC parallel RL, right? Here I can directly write the value of RO is equal to RC, right? Mention here without load resistance. So if you don't have any load resistance, resistance of the collector itself will act as a load. Parallel combination of collector resistance and load resistance will be output resistance, and that will be with load resistance. Okay, this was all about the output resistance. Fourth parameter that we have to find out as input resistance, and that input resistance you can easily dig out VI divided by II. If you go through this particular model, now I want from input side. So from input side, see, from input side, here your eyes are kept and you are getting only two resistances are connected in parallel, and that will be your equivalent resistance from the input side. So when we look from the input side, we will be getting the value of Ri as Rb parallel beta Re, right? So I can write directly the value of input resistance Ri is equal to Rb parallel to beta small r. This is without source resistance. Now if we place a source resistance, then picture will be like this. Source resistance always and always in series with your voltage source. So I can say that this is your R signal, this is your RB, which is nothing but R1 parallel R2, and this is your beta Re. Now if you look from this particular side, I'm just wanted to add this R signal, because this combination is in series with R signal. We can say that Ri is equal to R signal plus parallel combination of Rb and beta Re, right? This is your input resistance with source. So if we connect source resistance, then your input resistance, input impedance will get enhanced. Guys, keep this in mind that here I have implemented this all these formulas in the form of RE model. Now what you have to do, you just try out with different another models like H parameter model and R pi model. If we try to change this particular formulas by just changing the parameter with relationship between all these three models that we have learned in the last video, then we can easily implement in the form of R pi model and H parameter model. See, I'll give you one example. For example, your voltage gain in RE model is equal to, let's say, AV is equal to RC divided by small re minus, obviously. Now what we have to do, we have to get the relationship between small re and R pi, right? I know that, keep this in mind, I know that what is Re and what is R pi and what is Gm. I know Gm is equal to 1 upon Re, right? And we can get that 1 upon Re is already there in the formula. So why can't I use this Gm in my formula? So I can say, using, let's say, the equation number 2, equation number 1, using 1 and 2, we will be getting AV is equal to minus of Gm into Rc, and this is nothing but the voltage gain by using R pi model. Same R pi model you use, and by getting the R pi model, you do the analysis using AC analysis and you will reach to this particular formula without fail. Now if I want to convert that voltage gain into H parameter model, this is of R pi model. If I want to convert H parameter model, that means Re, I want to convert it into H parameters. So I know that by using Re, rather beta Re is equal to Hie, I can express this Re as Hie divided by beta. So we can say that Re will become Hie divided by beta, right? But I know that what is beta? Beta is HFE, right? See, if you are converting everything, then you have to have each and every parameter that should be there inside that particular model only. Not another parameter of another model should be there in your model. So beta is equal to HFE that we will implement over here. So I can say Re will become Hie divided by HFE, right? Just implement this in your first equation. Put in equation number 1. What do we get? That is nothing but your voltage gain is equal to minus HFE divided by Hie multiplied by Rc, and that is nothing but with H parameter model. Now similarly, you can also go for input impedance, output impedance, current gain with R pi model and H parameter model as well. So this is all about the AC analysis of CE amplifier without fail. Keep this in mind. This is with bypass capacitor. In the next video, we'll have to learn the AC analysis of CE amplifier only, but without bypass capacitor. So stay tuned for that. Learn more and more ADC along with me, along with Ekeeda videos. So subscribe Ekeeda channel. Thank you.